Nanotechnology is the science of modifying objects at atom or molecular level. Professionals in this field measure items in terms of nanometer, which is equal to 1 billionth of meter. We have discussed in the first lecture what is nano, why it is important, and from where this term is firstly used. So we have discussed several examples for that. In this present lecture, the part 2 of this emergence of nanotechnology, we will discuss few examples from pre-modern era where they talk about or they use some nanotechnology. Then we will discuss some experimental developments, some application of developments of nanotechnology in the recent 20-30 years. You will be able to learn a lot of things about nanoparticles, nanotechnologies here. The objective of this lecture is to give you idea that this is not the new subject. Even from the 4th century we are discussing this. We are using this. As far as the pre-modern era, we use these things. We use some properties, but we stop after some time. From the 18th century, we thought it again, but with the basic applications. Then, in the 20th century, with the development of quantum physics, we got the power to see small images. When we talk about dual nature of waves and dual nature of particles. With the use of optical light, we can see only up to 10,000 magnification. But with the advent of electron rays, this 10,000 extended up to lakhs, few lakhs. And that is why we thought on this. Can we go below this? As we have discussed in the last class, there is a plenty of room in the bottom. So we started this theory from the Feynman and we developed the things. There are several catalysts worked here. Transistor, development of transistors, development of network circuits that help a lot in developing this. Then we move to AFM and STM. These developments help a lot in thinking in this direction. Can we create the particles? Can we manipulate the particles? On the other side, some good literature created. Engine of Creation, Future Technologies from Dexter. They talked much about a fancy and dreamy view of the nanotechnology. So people motivated in this direction. We will discuss these things here. So as a learning outcome, you will learn about pre-modern examples from the nanotechnologies, development of last centuries, development of present centuries, initial stage of development, then how they have developed the sophisticated instruments, AFM, atomic force microscope, STM, and finally we will move to applications, how the Siemens group is working on this direction and how they are trying to create. They have given a target that in 2021 they can project a 3 nm FET device, which is smallest ever. So how they are working, and apart from these electronics, we have many applications, possible application, biology, in physics, in chemistry, in day-to-day application, hygienic application, health applications. So we will discuss a lot in this. At the end of this lecture, we will learn how this is developed and where to go, where to do work. Pre-modern examples of nanotechnology can also be cited. Early examples of these nanomaterials were based on craftsman empirical understanding and manipulation of materials. They use high heat as a common step to produce these materials with novel properties. Yes, whatever we know about this past age or the pre-modern age, then they might not have too much mathematics and too much science. They might not know these things. But even though they knew these things, they knew the understanding of manipulation of materials. They knew how the glass can change colors on heating, on addition of some other things, or to prepare these things in a different way. So if we move to pre-modern era, then we will see then many examples of nanotechnology. As you can see in this figure, these are the figures of windows used by the old era people. These colored windows, where we know now that they use gold, silver to change the colors. They knew the method of development of glass of different colors. One of the interesting example from the past is Lycurgus cup in Rome. This is an example of dichroic glass, two colors. It was assumed that this is from 4th century and made up of colloidal gold and silver. Colloidal gold and silver in the glass allowed it to look opaque green when lit from outside, but translucent red when sunshine through the inside. We have shown these images there. You can observe this green and red both dye behavior, which is due to colloidal gold and silver. This cup you can see in the British Museum, and in the next slide I am showing you a small video which is containing this cup. How interesting this is. This is one of the first example of existence of nano in the 4th century. Here you can see the cup. See this cup. This is the cup. This cup in British Museum. The glass appears from above, light sunshine outside, then inside looks like green. See. In 19th to 17th century, glowing, glittering, and lustrous ceramic glaze used in the Islamic world and later in Europe contained silver or copper or other metallic nanoparticles. In 13th to 18th centuries, Damascus saber blades contained carbon nanotubes and cementite nanowires, an ultra-high carbon steel formulation that gave them strength. So we can't say the NW developed recently. It has been used in Europe, in Islamic worlds, from anywhere, everywhere, from 4th century, then 9th century, then 17th century. There are so many examples you can obtain from here. Here it is shown the south rose window of Notre Dame Cathedral from 1250, example from the 13th century. Here we have shown some blades. The sharp objects. This contained carbon nanotubes and cementite nanowires. An ultra-high carbon steel formulation that gave them strength, resilience, ability to hold a niche. The Moir fringes were observed when we took this electron microscope of these blades, and they concluded that the possibility of nanoparticles there. The Damascus saber is photo by shown here. HRTEM is used to check these materials. Yes, interesting thing is we are searching, we are analyzing the old materials, and then we are concluding that nanoparticle was exists. But no written were blocked in all this. There are some examples of vibrant stained glass windows in European cathedrals, and this owed their rich color of nanoparticles of gold chloride and other metal oxides and chlorides. Gold nanoparticles also act as photocatalytic air purifiers. Now we knew this and we are working on this, but still it is very interesting to note, it is very surprising to note They have used gold nanoparticles in 6th century, 8th century, 15th century. So that is very interesting to us. Here I have quoted two interesting examples of discoveries and developments that enabling nanotechnology in the modern era based on increasingly sophisticated scientific understanding and instrumentation as well as experimentation. First was given by Michael Faraday in 1857. He discovered colloidal ruby gold and demonstrated that nanostructured gold under certain light conditions produce different colors. So that is the first thing given by Michael Faraday. So you can say even Michael Faraday started this word term in the modern sciences. In 1936, Mueller, working at Siemens Research Laboratory, invented field emission microscope, this allowing near atomic resolution image of materials. So these again are something that compel to move to the size at nanoscale. Human mind is very innovative. We want to search too many things. These are the inspirations that we have taken to move to nanoparticles range. Advances in interface and colloidal science also helped a lot. Interface and colloid science has existed for nearly a century before they become associated with nanotechnology. If you go in the past, we go in the 20th century, then we can see that the size measurements of nanoparticles have been made during the first decade of 20th century by Richard Adolph Zsigmondy, who also won the Nobel Prize in Chemistry in 1925. He made a detailed study of gold, soot, and other nanomaterials. Size at about 10 nanometer using ultra microscope. And this ultra microscope he developed was capable of visualizing particles much smaller than light wavelength. He also was the first person who first to use this term nanometer, explicitly characterizing particle size. So there are certain examples from the past also. In 1920, the Langmuir, who won the Nobel Prize later on, introduced a concept of monolayer, a layer of material 1 nanomolecule thick, that is called Langmuir-Blodgett films. In the 1950, the Abrikova and Dergaguin conducted the first measurement of surface forces also. So there are certain examples from the 19th century who started the work. We can also remember 1947 transistor Bell Labs. Burdeen, Shockley, and Walter Bratton, they discovered semiconductor and transistors and greatly expanded scientific knowledge of semiconductor interface. This development have given foundation to electronic devices and information age. So we can't forget this that in 1950, Robert Dinger developed the theory and the process of growing monodisperse colloidal materials. and ability to fabricate colloids enables myriad industrial uses such as specialized paper, paints, and thin films. In 1951, Mueller pioneered field ion microscope, as we also discussed in the previous class. This is to image the arrangement of atoms. In 1956, Arthur von Hippon at MIT introduced many concepts of coined the term molecular engineering as applied to dielectric, ferroelectric, and piezoelectrics. So these are the examples that can be deal, that can inspire us to develop new things. After the discovery of transistors and circuits, we moved to integrated circuits in 58 in Texas. The integrated circuits has given a new dimension to the semiconductor electronics, and then everybody thought about miniaturization of the circuits. That is why we move to use small chips, small devices, and all the time we searched about small circuits. In 1974, peoples from Finland developed atomic layer deposition for uniform thin films. They also developed synthesis and properties of semiconductor nanocrystals, and this leads to development of quantum dots in future. Nanoscale thickness was demonstrated in the gate oxide and thin films used as early as in 1960. So electronics is developed, then it moved to micro, then nano. So it has been done. But it was not until the 1990s the MOSFET with nanoscale gate was demonstrated. So everything was in learning stage. They developed the things, but in 1990 we reported this metal oxide semiconductors, field effect transistors. Nanotechnology and nanoscience especially got a positive boost in 1980. The reason was development of two major things. The one is scanning tunneling microscope, and the birth of cluster science. How clusters can help in many scientific applications. The development of STM helped a lot to see very small images. These developments led to the discovery of fullerenes in 1985 and the structural assignment of carbon nanotubes in 1991. Many things were developed, but to verify the size, to verify the nano size, there was a need of an instrument. That instrument was scanning tunneling microscope. The development of FinFET in the 1990s also laid the foundation of modern nano electronic semiconductor. The interesting thing about this is the nanotechnology took a lead in 1980 in many applications. Here we have shown Mohammad Atala and Dawan Kahang on the right side. These two demonstrated MOSFET with 100 nanometer gate thickness, oxide thickness in 1960, and nanolayer based MS junction transistor using thin film and 10 nm thickness in 1962. So these two persons also contributed a lot in this field. In 1962, Tala and Kahang fabricated monolayer based semiconductor junction. In these transistors, we used gold thin films with thickness of 10 nanometer. Gerd Binning and Heinrich Rohrer won Nobel Prize for the invention of scanning tunneling microscope. Scanning tunneling microscope gave huge strength to the material science, because using this we can develop many things. We can see the image at the edge of nanometer. STM basically an instrument for imaging surface at net atomic level. This was developed in 1981. In 1986, Binning, Kelvin, and Christopher Gerber invented the first atomic force microscope. Yes, within 5 years they have developed anyone that is atomic force. The biggest challenge with the STM is electron beam. You need electron beam. But then they develop AFM. It doesn't need any electron beam. They simply work on force. What force we are applying? After the imaging purpose, initially they have developed for imaging purpose, but in 1989, Don Igler also reported to manipulate atoms using STM. He used xenon atom to spell out IBM logo, and he got shared a very big prize for this one. Here you can see how Don Igler manipulated atoms and wrote IBM. It can only be seen through nano instruments like STM, because this is developed at nanoscale by manipulation of atoms. After the emergence in 1980 again, the field was growing, and in 2000 the field was subjected to growing public awareness and controversy in early 2000. The prominent debate about both its potential implication and feasibility of applications. Till today we have these controversy, whether it has some applications, yes or no. If it is there, what are the ethical issues involved, and how the application envisioned, how we will work with molecular nanotechnology, and how the government supports such type of great work. So many things have started in 2000. Soon after, many commercial applications were designed and developed. However, most of them were limited to bulk applications of nanotechnology rather than transformative applications. But it's a beginning, and we started work on this, we started thinking of things. As we have discussed yesterday also, the book by Eric Drexler, Engine of Creation, gave a lot of good feeling to the readers. As a technologist, it gave me a sense of calm. That is, nanotechnology showed us incredible path. If the nanotechnology was our future, then I didn't feel pressed to solve problem in the present. Would go to this book, this future, and I think we can enjoy life more better than this that we have if we use this book. If the vision of this book will fulfill soon. This is another book who created revolution in the field of nanotechnology, created by Drexler. This is a comprehensive easy to understand handbook that explains what is nanotechnology and how it will revolutionize life in the future. The world-leading expert Drexler examined the spectacular accomplishment that might result from a breakthrough, elimination of disease and pollution. How can we create low power solar energy and many futuristic developments related with nanotechnology? So this is another thing from where we have created revolution through books. Actually, the revolution created into two types, as we have discussed: revolution through books, through study materials, and through experiments. So I'm talking about books and both experiments. Discovery of fullerene is an again a very important milestone for the nanotechnology. Harry Kroto won Nobel Prize of 1996 in chemistry along with Richard Smalley, and Robert Curl for their discovery of fullerenes. The fullerene were discovered with these people. These are carbon-rich grains. The result of collaboration was the discovery of 360 and the fullerene as the third allotropic form of carbon. The subsequent discoveries also included androidal fluorines and their large family of fluorines in the following years. Fluorines are the cage structures of carbon, and the size of the structures help a lot in development of many applications in nanotechnology. Another discovery is discovery of nanotubes, carbon nanotubes by Sumio Lijima. Although carbon nanotubes have been produced and observed under a variety of conditions prior to 1991, this discovery of multi-walled carbon nanotubes in the insoluble material of arc-burned graphite rods in 1991, they developed if single-walled carbon nanotubes could be made, then they would exhibit remarkable conducting properties. This helped create initial buzz that now associated with carbon nanotubes. The development of various structures, carbon nanotubes, fluorines, gave a lot of new things to the field of nanotechnology. As we talk about what we have developed after the development of nanotechnology, yes, we have designed some initial commercial applications. And almost most applications are limited to bulk use of passive nanomaterials. For example, we have developed titanium dioxide, zinc oxide nanoparticles in sunscreen, cosmetics, food products. We are using silver nanoparticles in food packaging, clothing, disinfectants, and household appliances, such as silver nano, carbon nanotubes for silver stain resistant textiles, and cerium oxide as a fuel catalyst. These we have developed. As of up to March 2011, we have estimated about 1300 manufacturer identified nanotech products are available in the market. So it is continuously developing, but it is still we are in the initial stage. As we know that the commercial nano electronic semiconductor devices began in 2010. Then we have developed 16 nm processes. Then Samsung Electronics began production of 10 nm process, and then 7 nm, and then 5 nm, and so on. Now Samsung announced the plan for commercial production of 3 nm GAA FET process by 2020. So you can imagine how we are reducing from 16 nanometer to 3 nanometer devices continuously. Soon we will be able to produce this Samsung by the Samsung. That is why we are saying there are a lot of potential in this field. Developers. In this lecture, we have discussed about emergence of nanotechnology. We discussed pre-modern era. We discussed present era. What happened in the last century? Then what is the status in presently? What is developed in the form of publications and books? And then what are the development in experimental sites and industries outlook for this. Now these two lectures I think are sufficient to develop energy that this is one of the biggest field, on the most potential field, where lot of work is to be done. Whatever is done, it is in initial stage. So with this background, I am closing this lecture. Thank you.